So this week in lab, you're going to be taking a look at preparing a series of aqueous solutions with the ultimate goal of finding the concentration of sodium chloride in an unknown solution. Concentration of a solution is the amount of solute present in a given quantity of solution. And so in this week in lab, the solute is sodium chloride and the solution is a mixture of sodium chloride plus water. The solvent being the water, since it's an aqueous solution. Most common unit of concentration used by chemists is molarity, which is the moles of solute over the liters of solution. And so in this week in lab, you're going to be taking a look at the moles of sodium chloride over liters of solution. This video will walk you through the principles behind the calculations you're going to do in the lab for your pre-lab assignment and for the lab. So, big idea is if we are preparing a solution, we know how much stuff we're adding to it, so we can figure out the amount of stuff per volume. So if I want to determine the molarity of sodium carbonate in a solution prepared by dissolving 0.4 moles of the substance in 200 mils, I'm going to want to divide that number of moles that were given in the problem by the volume in liters. So it is often helpful with these types of calculations to convert the volume to one in liters at the beginning of the problem. So we'll take our 200 milliliters and multiply by 1 liter over 1,000 milliliters, since there's 1,000 milliliters in a liter. So this will become my volume. And then I can calculate my moles of sodium carbonate by liters of solution by dividing the 0.4 moles that we were told we had in the problem by the 0.2 liters. When I do this, I see I have 2 moles per liter, which is the same thing as saying 2 big M. Why don't you pause the video and take a look at this second problem? I will include the solution, the complete solution, in the notes for the video. So now that we've got a handle on dissolving moles of the substance in liters of solution, of course we never are measuring out moles of a substance, instead we're measuring out mass. So in order to determine the molarity of a solution prepared by measuring out something at the balance, like you'll do this week in lab, we can convert the mass of the substance. So if we're told that we have 25.67 grams of sodium phosphate and we add it to enough water to prepare 500 mils of solution, we can determine the concentration by first finding the moles of the sodium phosphate and then dividing it by the total liters. So note that there's 2 things we need to do before we can do anything useful. And this is what you'll end up doing in lab. Okay, so first I'm going to determine, for my plan, I'm going to determine the moles of my sodium phosphate. And then I'm also going to determine the liters of solution. And at this point, you know how to do both of these things because we determined moles from mass way back in chapter 2, right? So to determine the moles, we can take our 25.67 grams and we will end up dividing by the molar mass, because when we do that, grams cancels and we end up with a value in moles. And then I've got my 4 sig figs based on this value here. Liters of solution in this case, similar to before. I'll take my volume in milliliters and convert to liters by dividing by 1,000. Note that this week in lab we are using volumetric glassware, both pipettes and flasks, so it's important to include all of these zeros because they are all considered significant. This has important implications for the number of sig figs that I include in the answer. Because ultimately, my sig figs from the number of moles is going to be what determines the number of sig figs, not the volume of the solution. And this will be the case when you do the lab this week as well. When I do my division, I get 0.3132 moles over liters of sodium phosphate, which is the same thing as 0.3132 big M. Okay, why don't you try this second sample problem? And in the annotated version of the notes, I will include the complete solution for that as well. Finally, after we've measured out our sodium chloride, dissolved it in water to prepare the stock solution, we need to prepare a series of dilute solutions. So I'm going to introduce the concept of a dilution next. So stock solutions are typically prepared at higher concentrations that will be useful in a given reaction, because we don't want to prepare a new solution every time from a solid every time we want to do a chemical reaction. So typically we have a stock solution, and you're going to be making yours in a 250 ml flask. But for this example, let's pretend we made one in a 100 milliliter volumetric flask. I'm going to represent the solute in this case with little pink dots. So you could think about each one of these representing 0.1 moles of solute in this example. So I'm going to represent this. Let's say we had 5 dots. That means that we have 0.5 moles of solute. So if I wanted to calculate the molarity of my stock solution, so MI or M1, they mean the same thing depending on which textbook you're looking at. We would have 0.5 moles of solute. As before, we need to convert this to liters, so it's going to become 0.10000 liters. And so we can divide it by the 0.1 value. And when we do this, we get that there are 5 moles per liter, or 5 big M. They mean the same thing. I'm going to leave it in moles per liter because that's more useful for calculations. Now, let's say that I transferred this entire flask to a new flask. We don't always transfer it all, but let's say for this thought experiment that we did. So I've got a 500 ml flask, and we took the whole thing and put it in. I've still got the same amount of stuff. I've still got my 0.5 moles, but now they're distributed in a much bigger volume because I added enough water to bring it to the line in the new flask. So that means the overall concentration or number of moles per liter is going to be much lower. And we could calculate it, okay? We've been using 500 mils for a couple of sample problems, so we already know it's 0.50000 liters. And so we could calculate the molarity of this new dilute solution, in other words, MF, the final molarity, which I'll also use as M2. That's the same thing. This one we could calculate by taking our 0.5 moles and dividing it by 0.5 liters. And when we do this, we see we now have 1 mole per liter. So by diluting it, we have a much less concentrated solution than we did before. Note that we still have the same number of moles. To determine the moles in a given volume, you can always take the molarity and multiply by the volume. So for example, if we have the initial molarity and we multiply by the initial volume, we, for example, for our concentrated solution over here, we have 5 moles over liters and we multiply it by our 0.1000 liters. It becomes apparent that we have our 0.5 moles that we started with, right? So because this is true after the dilution as well, so if we have our 1 mole per liter and we have our new solution volume here, so this is V2 or VF, we could multiply it by this new volume. Here's the proof. We again have 0.5 moles. Since these are equivalent to each other, that tells us that we can always use this relationship, M1 V1 equals M2 V2, we can always solve for one of the variables given the other three. So I'm going to do one sample problem, and we're going to be using this equation a lot in lab. So I just proved to you that the initial volume of this concentrated solution times the volume that you transfer is equal to the final molarity of the dilute solution times the final volume of that dilute solution. So we can rearrange this for any dilution problem. So for example, if we how could 250 mils of 0.1 molar copper sulfate solution be prepared from a stock solution of 500 millimolar copper sulfate? So if we take a look, we're given some information about what we want. We're told that we want 250 milliliters of solution. So this is the volume of the dilute solution. That's what we want. And we're told that we want a molarity of 0.1 molar for this one. Then we're asked how much of the initial solution to transfer. That's what we're being asked to find in the problem. And we're told some information about its concentration. As given, this isn't terribly useful because this concentration is in millimolar and this one's in molar. I wanted to highlight that molarity is moles per liter. And there's 1,000 millimoles in 1 mole. And this is useful in biology in particular. Many units are given in millimoles per liter. So that's what little m big M means. So let's convert this to a value in molar so that the units will match. Okay, so I've got 500 millimoles per liter. I can multiply by the fact that there's 1 mole for 1,000 millimoles of anything. The millimoles cancel, so I end up with 0.500. Oh wait, those aren't significant, this one. So 0.5 moles per liter for my M2 value. Now, like I said, if we're starting with our equation, M1V1 equals M2V2. Note that this is the same exact equation as, the one that's given in your textbook. So initial molarity times the volume transferred of the stock solution is equal to the final molarity of the dilute solution times the final volume. These are the same equation, but like I said, I was trained with this one, so I'm used to the M1V1 equals M2V2, so that's just my instinct. So the volume that we need to transfer to make this desired concentration and volume of copper sulfate, I'm going to rearrange the equation to solve for the volume that I want to transfer. We know the other ones because they were given in the problem. So now I can substitute in that we want the new dilute solution to be 0.1 molar in terms of the solute. We want it to have a volume of 250 milliliters, and our initial concentration for the stock solution is 0.5 molar. When we do the calculation, we see we need to transfer 50 mils. Typically in this lab, you're going to do a series of calculations where you actually know the molarity of your stock solution, because you can calculate like we did before. You'll know which volume you transferred and the final volume, so you can do a similar rearrangement to find the molarity of each of your dilute solutions. The V1 in your case, or the initial volume transferred, is going to be the amount that you pipette into each of your flasks. And you can see from this little sketch that as you increase the amount of stuff that you add to it, so the number of moles, you end up having a more concentrated solution, like this case where there's dye. It looks darker because there's a higher molarity solution. And because of this, we end up with a higher signal than for the lower molarity solution. If we know the properties, that a property that corresponds to concentration, so in your case, the specific gravity is what you're going to measure, you can make this plot relating specific gravity to the concentration. And in your case, it will be in molarity. In this sketch, it was in milligrams per liter, but those are both just concentration units. Then you'll be able to, for an unknown solution, use the equation of the line to figure out what the concentration of the unknown solution is.